if you've been here since yesterday, if you attended the talks yesterday, if you raise grass-fed beef, if you're considering raising grass-fed beef, you might already be familiar with many of the environmental benefits that come with grass-fed beef production. Yesterday you heard about all of the beneficial insects that are encouraged by perennial cover on the ground, by intensively managed rotational grazing. You've talked a little bit about the impacts of increased soil organic matter and all of the environmental benefits that has, such as reduced runoff, increased infiltration rates, increased cation exchange capacity, so you can hold more nutrients in the soil. All of these things are things that come along with well-managed rotational grazing, which many of you raising grass-fed beef are already doing. What I want to talk about is, just like any system, a grass-fed beef system also has some leaks. And the good thing to know is that management can actually help plug these leaks. So what is an environmental footprint? Have any of you in the room heard of environmental footprints, just by a show of hands? Okay, a fair number. For those who haven't heard of environmental footprints, they're basically just one metric of sustainability that allow you to look at all of the inputs and all of the environmental emissions that are associated with the production of any product. That product could be 1 pound of beef, it could be a plastic bottle, it could be a watch. This is a metric that you create through what they call a lifecycle assessment, which is really a tool from industry that they use to analyze their processes and to improve them. So in recent years, lifecycle assessments have been applied to biological systems. And because of that, they're not a perfect metric, but they can give you useful information that you can use to improve your management processes. So if we were gonna conduct a life cycle assessment for a grass-fed beef operation, like what I'm doing, you would first look at the beef operation itself. So as you can see, on a grass-fed beef operation, you've got feed production, you're growing grass to graze. You might be harvesting some of that grass for hay or silage. You've got animal production, so you're raising animals. Animals are growing, you're breeding animals. There's an animal production process. And then you may have manure handling. So up here in the Northeast, by a show of hands, how many people here are from the Northeast? Okay, maybe about half of us. In the Northeast, many of us have to feed during the winter, whether that's silage or hay. And there are a lot of different ways of doing that. Some people may feed out on pasture, some may bale graze, some may feed in kind of a dry lot or a barn. So you may have some manure handling, because eventually you may have to scrape that area and put the manure back out on pasture. So when I'm thinking about an LCA, I'm going to think about all these processes, and I'm going to create basically a really complex Excel spreadsheet where I put in all of the data about the inputs and outputs to each of those processes. Then I'm going to say, okay, what are the inputs to the farm? So in a grass-fed beef operation, it might be fuel. You're using some electricity, maybe if you've got a barn, or if you've got freezers on the farm. There may be fertilizer use, although in my surveys of Pennsylvania, fertilizer use seemed to be it wasn't very common on people managing perennial pastures. Fertilizer use was more common when they were grazing annual pastures or seeding annuals into cool season pastures. And then you may be buying plastic to bale silage. You may be purchasing bulls or other animals that you bring onto the farm. Each of these inputs is something that I would include in the spreadsheet that I'm using to conduct my life cycle assessment. Then I'm going to have outputs. So there may be beef that's sold from the farm. There may be animals that are sold. Maybe if you've made excess feed, you may sell that. And then you may export manure, which this is more common, in a dairy scenario, but you may export some manure. So I'm going to keep account of that in the spreadsheet as well. Now, in addition to the inputs and outputs from the farm, there are some emissions to the environment. So at this top box that I'm circling here, these are emissions that are going to the air. So you've got some carbon dioxide, some methane, some ammonia that's going to be emitted from the farm. And then you're going to have some nitrogen and phosphorus that might be lost from the farm. In addition, in the process of producing the inputs that go into the farming system, there's going to be some emissions to the air and some emissions to the water. So in this spreadsheet, we're going to try and quantify what might those emissions be. And all of this is based upon the type of management that you're using on the farm. Once I've completed that, then I basically take all of those inputs or all of those emissions and divide that by all of the beef that's produced by the farm. And that gives me an environmental footprint. So in some ways, you could look at this as a metric of environmental efficiency. It's what were the environmental emissions per pound of beef, or what were the inputs used per pound of beef that was produced on the farm. So what I'm going to show you today are the life cycle assessment results from 2 Pennsylvania farms. The first is a farm that's purchasing all of the supplemental feed that it needs. So the management philosophy here may be that, you know, I'm a really great grazer, I can do a great job grazing this land, and I want to only purchase feed. So I'm gonna purchase feed, and I view that as not only a supplement for my animals, but also a way to feed the soil. So I view it as a source of soil fertility. That's what System A represents. System B is a system that is making all of its supplemental feed on farm. So maybe you have machinery, you're really good at making high quality hay, and you decide, okay, the only nutrients I want to leave this farm are gonna be in the meat that I sell. So that's what System B represents. From the survey data, the only way that these two systems really differed was in the stocking rate. So the system that bought all of its feed was able to operate on a slightly smaller farm than in System B, so that's why I've got it highlighted in red. And then, of course, in Pennsylvania, the most commonly purchased supplemental feed was hay, and the most common feed that was made on farm was hay. So in these simulations, this is what I'm assuming. They're both 25 cow herds, and they're both finishing cattle at about 24 months of age and 1,100 pounds. So the first footprint I want to talk about is maybe the most sinister of them all, and this is the carbon footprint. So the carbon footprint is really just a metric that estimates what were the total greenhouse gas emissions emitted in the process of producing 1 pound of beef. And why do we care about this? The reason why we care about this is because in the atmosphere, there are greenhouse gases. The ones that are important for agriculture are carbon dioxide, methane, and nitrous oxide. And under a natural greenhouse effect, the sun radiates energy down to Earth. Some of that energy is reflected back from Earth's surface and trapped as heat in the atmosphere. And these greenhouse gases enable that trapping to happen. So this trapping is actually very important for life as we know it. It supports the climates that we know, it supports the types of life that we know. And so to some extent, this is a good effect. We need this greenhouse effect to live life as we know it. But under the human enhanced greenhouse effect, there are certain activities like the burning of fuel when we're driving cars that increase the amounts of carbon dioxide, methane, and nitrous oxide that are in the atmosphere. And when the amounts of those gases increase, more energy is trapped in Earth's atmosphere, which shifts our climate systems. And what you end up seeing is that we have things like the hurricanes that have been happening in the Caribbean, the hurricanes that hit Florida and Texas. Those aren't new. Hurricanes aren't new, but what you see is that you have more hurricanes more frequently and they're more intense. So this is why people care about carbon footprints. And agriculture definitely is not the only industry that's emitting greenhouse gases, so I want to make that clear. There's an effort by all industries just to take a look at how many greenhouse gas emissions are they emitted and where can they reduce them. So this graph is going to show you the total greenhouse gas emissions for System A, which is the one that was purchasing all of its feed, and System B, which is the one that was making all of its feed. On the y-axis, I have it from 0 to 100%. So the carbon footprints between these two are actually very simple. I don't want to compare the two. I don't want to say one system's better than the other because each of you does what you do for a reason based on the resources you have available and your expertise. What I want to show is what contributes to the carbon footprint, and then later during the question and answer and discussion, we can talk about what might you be able to do to reduce the contribution of that part of your operation to that part of the carbon footprint. So in System A, and this will be the same for System B, the greatest contributor to the carbon footprint is from the animal. That's what this box is showing you here. And that is because the animal consumes feed, the microbes in the rumen digest that feed, and they produce methane as a byproduct of their digestion. It's a natural process that's been going on for a long time. The next contribution to the carbon footprint is very small. I don't know if you guys can see this very small black block, but that represents manure. So when manure hits the ground, it's exposed to the air, and there's a small amount of nitrous oxide and methane that's emitted from that paddy. In a grass-fed system, greenhouse gas emissions from manure are very small. But if we were dealing with a situation where you're managing manure like in a lagoon, you would have anaerobic fermentation going on. You'd have much more methane and nitrous oxide emitted from the system. The next contribution is from the land. So this is just a bit of nitrous oxide that's going to be emitted from the land when for example, during nitrogen fertilization or in the process of nitrification and denitrification, there'll be some nitrous oxide emitted from the land. There's a little bit that comes from fuel combustion. So just in the process of running a four-wheeler or running a tractor, there are CO2 and nitrous oxide, small nitrous oxide emissions from that. And then finally, a small contribution that we're calling pre-chain. And pre-chain just refers to any of the inputs that were purchased in the system. So in this case, this is mostly the feed that's purchased by System A. There's a small carbon footprint associated with that, and so that's about 10% of the total carbon footprint in System A. So you're gonna see that System B has a very similar breakdown to System A. The animal is the largest contributor to the total carbon footprint through methane. And then in this case, you'll see a slightly smaller pre-chain contribution, and that's just because System B is making all of its own feed. All right, the next footprint I want to talk about is related to reactive nitrogen loss. Reactive nitrogen is called reactive because it reacts once it gets into the environment. Nitrogen is a very leaky nutrient, as you all may know, and so it can be hard to keep it in the soil and the forage and the animals where you want it. And there are three major pathways of loss for nitrogen. The first is the animal grazes the forage, they digest it. The excess that they don't use is excreted in the dung and the urine. So from that urine patty, like I mentioned earlier, you can have some nitrogen that gets lost as nitrous oxide and a little bit that gets lost as ammonia. You can also have a little bit of that nitrogen lost in runoff, though in a grazing system, especially a well-managed grazing system, erosion is very low, so you lose very little nitrogen in runoff that way. And the last leaching, which is the most important one for grass-fed systems, I'll show you, is in nitrate leaching. So when that paddy's on the ground and you have a rain event, that nitrogen is going to percolate down through the soil profile, and some of it will stay there and be used by the forage, but some of it is going to go down past the root zone and end up in the groundwater, potentially. And this is in the Northeast, particularly where we're grazing very lush, cool season forages. This is the major source of nitrogen loss in these systems. So here again, it's a similar graph to the last time. The x-axis is from 0 to 100%. And System A is our system that's purchasing all of its feed. You'll see that about 25% of the nitrogen footprint for System A is lost as ammonia, and that's coming from urine spots, mostly in the pasture. So the animal is going to urinate on the pasture. Some of it makes it in. Some of it's going to spray on the leaves, and once that urine is exposed to the atmosphere, some of the nitrogen will volatilize as ammonia. This is about 25% of the footprint, but it's not a huge concern from grass-fed systems as a total emission. You'll see that a much greater proportion of the footprint, about 40%, is lost by leaching, and that's just nitrogen that went down past the root zone. About 10% is lost through denitrification. That's just the loss of nitrous oxide from the manure paddies, and then also from the land. There's a teeny tiny bit of nitrous oxide loss from fuel combustion. That's just from riding your four-wheeler around or driving the tractor, although in this case, this would be from riding the four-wheeler on the system that's purchasing all of its feed. And then there's about 12%, 15% that's lost pre-chain. And again, pre-chain are the emissions associated with any purchased inputs. So in this case, this is largely coming from the purchase of feed to feed the animals. The nitrogen footprint for System B, which is the system that's making all of its own feed, is different than the one from System A. There's a larger ammonia loss here, but a smaller leaching loss here. And again, this just refers to the nitrogen that's lost once that urine or that manure paddy hits the ground. The next biggest block here is from denitrification. So in System B, where the system is making all of its own feed, some of the land that's being cut for hay is also being grazed, but some of the land that's not being cut for hay is not being grazed, so it's getting a little bit of fertilizer. And some of the nitrogen that's being lost here is from that cropland. When I go in and I look at grazing that cropland, this loss is actually reduced a bit, and then you get more losses from leaching as a % of the total reactive nitrogen footprint. There's a tiny bit lost from fuel combustion, and then a teeny tiny bit lost from pre-chain sources, which makes sense because System B is not importing feed, it's making its own feed. So finally, I want to talk about the fossil energy footprints and the water energy footprints, and I'll probably go a bit faster through these two. So, 4 or 5 minutes. Thank you, okay, great. So System A and System B, I'm going to show you them at the same time, because what I want you to see is that not only I want you to know the footprints are very similar, And the breakdown of where the emissions are coming from are very similar. But the thing that I want to show you the most is that the majority of the fossil energy footprint for System A and System B comes from pre-chain sources. So this is fossil fuel that's being used in the production of things that are needed for the farm. So what does that mean? I mean, you don't have a lot of control over this, right? Because you're not controlling the management of those inputs that you're buying. But you can, the way that you would be able to adjust, I guess, how much of your footprint is associated with these pre-chain sources would be by sourcing from people or places that are not using as much fossil energy to produce whatever input it is that you're purchasing. The other major contribution to the fossil energy footprint is through feed production. And again, this is just from riding the four-wheeler around, maybe to fix fence, to move fence. And in the case of System B, where it's making its own feed, it's in riding the tractor around to make hay, put up feed, or feed animals in the winter. Finally, the water footprint is also very similar in its breakdown between System A and System B. Up here in the Northeast, most of our agriculture is rain-fed. There's a little bit of irrigation in Delaware, but in Pennsylvania, our grass-fed beef production is rain-fed. So the water footprints themselves are very small, and they're very similar between both systems. And the majority of the water footprint is associated with water used for drinking by the animals. If we were in a situation where we were grazing irrigated forages or we were feeding irrigated forages, you would see that a much larger contribution to the total water footprint would come from that irrigated feed. So typically the major source of the water use in beef environmental footprints comes from irrigated crops that are fed to cattle. Okay, so what does all that mean? In conclusion, in summary, the environmental footprints that I showed, so the carbon, the energy, the reactive nitrogen, and the water footprints are very similar between systems that purchase all of the feed that they need and systems that produce all of the feed that they need in Pennsylvania. In systems where you're purchasing your supplemental feed, the major thing to think about is nitrogen losses through leaching. And those can actually be mitigated through improved forage management practices that increase total forage production, as well as increased soil organic matter. And I'll do a little bit of exploration of this in my analyses for my dissertation. If you're in systems where you're producing all of your supplemental feed, the nitrate leaching was also the major source of nitrogen loss. And again, that can be mitigated through improved grazing management practices. And also, if you're in a situation where you've got fenced hayland that you're not grazing, or that a person's not grazing, grazing that hay crop actually reduce the nitrate leaching losses a bit from that land. The biggest thing is, between these systems, because the environmental footprints are very similar, you choose a system that works based upon your expertise, your available resources. And remember, just keep in mind that in a grass-fed system where you're grazing lush, cool season forages, the animals are getting a lot of crude protein. The major nutrient that's going to be leaking from the system is nitrogen. So with that, thank you for your attention, and I'll turn it over to Dr. Roundtree.